So this is section 1.5 for business calculus, and we're talking about limits. So I wanted to just do a couple graphical examples before I move to the worksheet that I sent you that I'm going to go over. And the idea of a limit is this. When you're graphing a function, there are times where the function has an asymptote, a vertical asymptote that it can't cross. There are times when the function has a hole in it that keeps you from being able to draw it continually. You have to hop over a hole. And there are piecewise functions that can have a function change at a certain x value into a totally different function. So if you put all that together, the idea of a limit is this. If you are on the function, so pretend that you are standing on the function and walking. Every time, as you're walking along the function, every time you stop, you're going to stop at a certain x value, and then it's matching with a certain y value, and that's a point on the function. If you come across an asymptote, you are going to keep going up and up and up and up and up on your function. You wouldn't be able to cross that asymptote. And so if this is an x value, let's say this is the x value 6, and you want to know what happens to your function as you approach an x value of 6, you would say your function just gets bigger and bigger and bigger and bigger. From the left you can see it right here. You're coming along your function and you just keep going higher and higher and higher and you never stop. From the right, the same thing happens here on the picture I drew. Just keeps getting more and more and more and more. So what you would say in limit notation is the limit as x approaches the value of 6 of your function is infinite. It's not like a particular point on your curve that if I try to approach maybe the value -1 here, I'm going to get a y value of 2. I'm on the curve, and the limit on the curve is just going to be the function value. But sometimes you have infinite limits. Other times, let's say this is the value 8. Well, if I'm on the curve and I come at the value 8 on the x-axis from the left or the right, I can't quite get there because it's a hole, but I can get as close as I possibly can. And the limit will be whatever this function value is on the y-axis. So let's say that's the number 3. I would say the limit as x gets closer and closer to 8 from either the left or the right is 3. But the function value of 8 does not exist. It's a hole in the graph. There's no function value there. But there is a limit, a limiting value of 3. It's what I'm getting closer and closer to on the y-axis as my x values get closer and closer to 8. And then finally, if I look at what's happening here on the piecewise function where it's breaking apart, I could say that the limit as I approach 10 from the left actually has a value. When I approach 10 from the left, I'm coming here on this piece of the function, and whatever this value is where the dot is, let's say it's 3.5. If I ran it back to the y-axis, I'd be at around 3.5. That's the limit as I approach 10 from the left. As I approach 10 from the right, we put a little plus afterwards to say 10 from the right, I'm going to be at a different point on the y-axis because I'm going to be coming this way, approaching 10 from the right. I'm going to be way down here. Maybe that's a y value of 1. It doesn't matter if it's a closed circle or an open circle. I'm still approaching that y value. And if that's the case, then I say the limit as I approach 10 of my function does not exist. Because if the limit from the left and the limit from the right aren't the same, it doesn't exist. So graphically, that's what we're looking for. If we are on the function and walking down from the left or from the right, are we getting closer and closer to a certain y value? Or are we blowing up to infinity? Or when we come from the left and the right, are we not matching and coming to the same y value? And if that's the case, there isn't a limit. And so that's what we're going to be looking at with this worksheet. So this is the worksheet that I emailed to you. And it's a worksheet on section 1.5. There's another one that has things a little more broken down that I'll allude to as well. So if you look at the picture and I say find the limit graphically, what I mean is if this is the x value of 1 and this is the y value of 2, because this point where this hole is the point 1, 2, you should be able to say that the limit as you approach 1 from the left, meaning you're coming at 1 from numbers like 1/2 or 3/4 or 5/6, if you were on the line, you'd be walking up this way. And as you got closer and closer to the coordinate 1 on the x-axis, you'd be coming closer and closer to the coordinate 2 on the y-axis. And the same would be true if you stood up here and you walked down. So coming from the right or the left, you have a limiting value of 2 for your function, which means the limit as you approach 1 either way is 2. However, and that's what these 3 dots mean, let's not even use them. Let's just say, but f of 1 does not equal 2. F of 1 does not exist. And that's what the hole means. There's a hole in your graph there, no function value, but there is a limiting value of 2. Graphically on this, same idea. If you approached x value of 1 from the left, you'd be down here on this piece of the piecewise function, where your x values are less than 1. And so the limit of that function is this y value, -1. But if you approach that x value of 1 from the right, so you're up here walking along the function, you're on a totally different piece of the function that has a limiting value of 1. And in that case, you'd have to say, for this particular function, the limit as you approach 1 doesn't exist, because they don't match left and right. And finally, here's another picture with a hole in it. The hole doesn't come from algebraically having a factor in the denominator. The hole comes from a piecewise function. And so because this function is the function y equals x, which is this 45-degree line, everywhere but where x equals 1, I have to put a hole there to drop out an x value of 1 on that. But this second piece is what fills in the hole. Y is supposed to be 0 when x is 1, which means there should be a dot down here that is this piece of the function. The function value is a single value when x is 1. In that case then, if you plug the number 1 into this function, you're going to get 0 out. But the limiting value of this function, when you come from the left or the right, coming at it from the left, coming at it from the right, is still this function value of 1. So in the first example, there isn't a function value when you plug 1 in. The second example, there is a function value when you plug 1 in, but it doesn't match the limiting value. And we're going to get more into that with section 1.6. What I have on the bottom of this page are all the limit rules from the textbook. However, since we're not together face-to-face, I'm not going to go through them one by one. I'm going to show you more on the flip side what the problems would look like that you'd need to solve. And then those rules will come up as we look at these examples. So, the first thing you want to know is, on any limit problem, I want to plug in the value x is approaching and see if plugging it in is going to give me the answer that I want for my limit. So in example A, I'm going to plug in the number 1 where x is in the numerator and the denominator and see what happens. In this case, 1 squared minus 1 over 1 plus 1 is 0 over 2, which is 0. And if this value exists, then that's my answer. The limit as x approaches 1 on this particular function is 0. But if I try that on B, I plug in negative 3, I'm going to get 9 minus 3 minus 6 over negative 3 plus 3. And that's going to be 0 divided by 0. And 0 divided by 0 is a number that does not exist. And so what I have to do in a situation like that is try to do some kind of algebra on this so that when I plug negative 3 in the next time, this doesn't happen, 0 over 0. The algebra that works here is factoring. You know that x squared plus x minus 6 factors into x plus 3, x minus 2. And the denominator also has a factor of x plus 3. So as long as I don't let x take on the value negative 3 before I divide out, which I'm not doing when I'm just getting closer and closer and closer to negative 3, I'm not actually getting there, I can divide those two factors out, and the limit as x approaches negative 3 of the function is going to be the same as the limit as x approaches negative 3 of x minus 2. Because you know when factors divide out, it means there was a hole in the graph, and dividing the factors out fills in the hole, and in this case it fills in the hole with the number negative 5, which is your limit. So using factoring to divide out to keep it from being 0 over 0 is one of your strategies to use in your homework. Another strategy to use, because in this case if we plug 3 in, we're going to have the square root of 3 plus 1 minus 2, which is 0. And we're going to have 3 minus 3, which is 0. So again, this is undefined. It's not an answer. I need a different kind of algebra for this, and this algebra is to rationalize. And that's why we learned how to rationalize the numerator for our last quiz. So what you're going to do to take this limit is you're going to multiply by the conjugate of the numerator, which is the square root of x plus 1 plus 2. And we're going to multiply numerator and denominator by that and get x plus 1 when these two multiply, minus 4 when those two multiply. We're going to have an x minus 3 and then the conjugate in the denominator. But what the numerator is going to simplify to is x minus 3. And we can divide that with the x minus 3 on the bottom. And once we do that, we can again take the limit. Because now that those are divided out, it won't be 0 over 0 anymore. It'll be 1 over the square root of 4 plus 2, or 1/4. So the conjugate is going to allow us to get that factor to divide out. For D, you have to know how to deal with an absolute value as a piecewise function. And we've talked about it, but I'm going to show you one more time here. That if you write the absolute value as piecewise, it looks like what's inside the absolute value if x is greater than or equal to 0. If you plug positive numbers in, you don't need the absolute value. Or if you plug negative numbers in, you're going to get the exact opposite out of the function. So we're going to rewrite our absolute value piece as a piecewise function, which allows us to rewrite our function as piecewise, as either 2x over x if x is greater than or equal to 0, or negative 2x over x if x is less than 0. So this will allow us to think about what the limit is from the right versus the limit from the left. Because the limit from the right means that I'm going to be plugging in values that are greater than or equal to 0. I'm going to be plugging into 2x over x, which is just going to give me 2, no matter what. My x's are going to divide out. But if I come from the left, I'm going to be plugging into the other piece and getting a limit of negative 2. So if you have to come from the left and the right on an absolute value, you need to rewrite it so you know what piece to plug into. So for E, when it's already written as a piecewise, if you're asked the limit as x approaches 1, you always have to come at 1 from both the right and the left. Because 1 is where this function is breaking apart. And I need to see if those two pieces are coming together at the same point in space or not. That's what's going to determine whether there's a limit or not. So when I approach 1 from the right, I'm coming at it from numbers greater than 1, so I just pointed to the wrong spot. Coming at it from numbers greater than 1, so I want to be plugging into this piece of the function. When I come at from the left, I need to plug into the other piece of the function. And when I plug in the number 1, I get 4 minus 1, which is 3, or 4 minus 1, which is 3. Because I get the same value, then I can be sure that the limit as I approach 1 of my function is 3, from the left or from the right. Without all that work on the test, you won't get full credit. You need to show me you know that I need to come from the left and the right to get a limit on a piecewise function. And finally, what happens if you plug in the value 2 and you get 3 over 0? Well, 3 over 0 also doesn't exist. But because you have a number that's not 0 over 0, that means that this limit doesn't exist because you're hitting an asymptote. So the limit of 3 over x minus 2 does not exist. And actually, you have to think about the fact that you are coming across an asymptote, which means you could be increasing on both sides, decreasing on both sides, increasing and decreasing. There's a lot of different ways that you can hit an asymptote, but however you do, you're not going to hit a limit. So the one time that you can say the limit does not exist is if you plug in and you get a number that's not 0 over 0. If you say does not exist when you get 0 over 0, you're absolutely wrong. So there's a couple examples on the broken down worksheet, And the reason I did this worksheet was for people who needed a little more help on these kind of things. So I solved what do you do if you have a function with no holes or asymptotes? What do the limits look like? Well, with no holes or asymptotes, you plug the value in, you get your limit out. It's very straightforward. What do you do if there is a hole? Well, if there's a hole, there will be a factor that can divide out, and you need to divide that factor out before you can plug the value in. The factor might be straightforward, like it is here, or it may be that you need the conjugate to find it, like we did on the last sheet. But if there's a hole, there will be a limit, okay? And that's a common mistake, that people see 0 over 0 and say no limit. If there's a hole, which means you got 0 over 0, there will be a limit. You just have to do the algebra to find it. If there's an asymptote, so there's a factor in the bottom that will not divide out with the top, that's when the limit doesn't exist. I go through how to deal with a piecewise function, which could be written as a piecewise function, it could be written as an absolute value. And I show this example of how if I ask you for a limit as x approaches 3, you have to come from the left and the right and see if you have a match. And that's broken down again with words that explain it. Another example of a piecewise is here too, to give you another example when from the left and the right doesn't match, and you say it doesn't exist. On the test, when you're doing these, you need to show me which piece you're plugging in from the left and the right. Okay, there's got to be this work involved, and that's why I gave you this worksheet with it all broken down. And another example of if I give you an absolute value, you have to realize it's a piecewise function. So you need to write it as a piecewise function and explain to me how you come from the left and the right if you're going to find the limit. So again, this second worksheet is just broken down step by step to try to give you a little bit better idea of how to go about these limit problems in your homework. And we will have time to go over questions on them the next time we meet, but feel free to email me or text me if you have any problem with the WebAssign, and I will try to help you through it before we see each other.